Hey Amira,
Hello.
how are you today?
Good. How are you?
I'm doing fine. How did the midterm go for you?
It's actually this week.
Oh, it's actually this week. Oh, but
Oh
what
wait,
about
like
the first one? The
the
first,
first one. The first one.
yeah.
Oh, it wasn't too bad. It
Oh,
was
that's
good.
good. I heard the average
Yeah.
is like 84%, like around that. Oh no, that's something else. That's the different class, I think. Or what was the average
I
for what?
think the average was 70s.
Oh, 70s. I
So
see.
I got better than the average. So
Oh, that's
that's
good.
good. Yeah.
Yeah. This is his grading like the regular grading scale, like 90 to 100 is like an A, 80 to 90 is like a B, 70 to 80 is like a C, or is it like lower? Like
No, I think it's just like that.
Oh, it's just like that. Okay, okay.
Yeah.
No curve, right? Because like the averages are like pretty high.
He said he's gonna determine whether we have a curve at the end.
Oh, yeah, yeah,
Yeah.
yeah. To see the averages
So
and everything.
yeah, based off the averages.
Yeah, that's good.
Yeah.
Yeah.
Okay.
So, are there any topics or practice problems that you want to go over for
Yeah,
this?
so I worked on the practice midterm today,
Mhm.
and then I had a question. So like on question one.
Oh, can you email me the practice question to brianochem dot I mean at gmail.com?
Yeah, sure. Wait, let me see. How do I do this? Okay, so, um, no.
Hey, Deshaun.
Sorry, what was your email?
brianochem at gmail.com.
Okay.
Yeah.
Hello. I think Amr will be down soon in like a minute.
Okay, okay. Sounds good. Hey, Katia. Katia.
Hello.
Yeah, how are you doing?
All right. How are
Yeah,
you?
doing fine. So what we'll do is we'll do Amira's question and then Darshan's question and a Katira question and we'll cycle through there. Okay, like that.
Okay.
Right.
Sounds good.
Different classes. Chem 1 and A, Chem 1 and C, and Chem 8A. Yeah.
I just sent it to you.
Okay, let me see.
It's from my iCloud.
Yeah, let's see.
Okay.
Okay, okay, I got it.
Okay, cool.
Let's see. Ability. Add to note, import, open, share screen, start. Okay. Okay, so which question did you want to start
I have
off
a few
with?
I have a few questions, but we can go with number one first.
Yeah.
So on the fourth part, um, so like when the H is not like in the vertical position, you have to rotate 90 degrees, correct, right?
Wait. Let me read this question
Oh,
first. Which of the below correctly sorts the priority groups when determining absolute geometry of a molecule? So is this assigning R and S like selecting the most like highest
yeah,
priority? Okay,
yeah.
great. So the very first thing you do is look at the very first atom attached to the chiral center. Right. Ignore every other atom. It's the very first atom that takes priority. Right. So what do you think about this problem? Like what's your guess here for this answer or for this question?
Well, I put S, but the answer is R.
Oh wait. Are we talking about this question here? For
Oh no, sorry, question one.
question one. Sorry, sorry.
Question one, like part four, like the fourth part.
Oh, okay. Wait. This one.
Sorry.
No, it's okay. It's okay. It's okay. Oh, so this is Fisher projection right here, right?
Oh yeah, yes, yeah.
Do you know what the horizontal lines are? Like, are they wedges or dashes?
Horizontal's wedged.
Wedge, right? Think of it as a Fisher projection as a person reaching out for a hug. Like the horizontal lines are the arms reaching out to you, like towards you for a hug, right?
Right. Okay.
The vertical lines are gonna be dashes.
Mm-hmm.
So now what is the highest priority group here?
Uh, BR.
Br, right? Because that's the highest atomic number, and then
Yeah.
Cl, and then carbon, and then hydrogen. Where do you want the lowest priority group to be at
In, in the dashed
in the dash,
area.
right? But what
Yeah.
do you notice about that here?
It's the hydrogen isn't.
Yeah, if it's a wedge, right? Do everything
Yeah.
normally. So one, two, three, going this way. What is that like right now? What does it look like?
That would be S.
Looks like S, counterclockwise, right? But you have to
Mm-hmm.
flip it. So it's actually R.
Right. So let's say like I like moved H. it's always going to be like the opposite then, right? It'd always
Yeah.
be okay.
If the lowest priority group is on a wedge, do everything normally and then flip it at the very end.
And then it would
Right.
be the opposite. Okay.
And then that would be the answer. Yeah.
And that would be for like any case, even if it wasn't Fisher projection, or
Yeah, that will be for any case. Even if it's not in Fisher projection, it could be in bond line form as well. Have you gone over this example where the lowest priority group is not a wedge, like it's on a flat bond? Like for example, let's say we have something like this.
yeah, I get kind of confused with that. Can we go over that?
Yeah, right. So if the lowest priority group, which is hydrogen in this case, is not a wedge or a dash, you can't do that trick. You can't do everything normal and then flip at the end. You have to do something extra if the lowest priority group is in a flat bond. What you have to do is rotate these three groups here. So I'm going to keep this other flat bond stationary. Keep it still, stay still, right? And I'm going to rotate these three groups right here, the hydrogen, methyl, and alcohol there. We know that we want the lowest priority group to be a dash, so I'm going to rotate it like this. Does this make sense so far? Like how I'm rotating those three groups? Like I'm rotating the H to the dash, the methyl to the wedge, the alcohol to the flat bond. Does that make sense so far? Right. So then once I do that, this side stays the same. I'm keeping that stationary. The flat bond is now the alcohol because I moved it there. The dash is now the hydrogen. The wedge is now the methyl. Notice how the flat bond, dash, and wedge stayed the same. It's just the groups that changed, right?
Correct. Yeah.
And then from here, you can do the regular RNS, which would be what in this case for practice.
It would be S.
Right. 1, 2, 3. Going counterclockwise. S. That's right. Let's see if you would get S without changing anything here, because sometimes you do get it, sometimes you don't. This depends on the molecule. Let's see. 1, 2, 3. Right. In this case, if you do it without rotating it, you get R, which is not correct. Right.
Okay. So.
Uh-huh.
So when you know how we like change the molecules around? So when I got S, that's going to be the answer. Like it's not going to be like R, right?
Yeah, it's going to be exactly S because the lowest priority group is already on the backside. That's the most important thing that you want to do and look out for when you're assigning RNS. The lowest priority group on the backside, the dash.
Okay.
Hey,
Wait,
Omar.
my confusion is like for the Fisher projection.
Fisher projection, right. So
it was the opposite. Like I kind of get confused.
Right. So in Fisher projection here, we only have dashes and wedges. Right.
Okay.
So if the lowest priority group is on a wedge, you can do everything normally. You don't have to do any rotation. Do everything normally, and then that's when you could flip it at the end. So if the lowest priority group is on a wedge, do everything normally, and then flip it at the end.
Oh, so I don't even have to like rotate the hydrogen to the where the CH is and like move the Cl to the Br, and then I get like S, and then I would just choose R instead.
Yeah, right. If it looks S, it's not going to be actually S because the lowest priority group is not a dash, the backside. So it's actually going to be R instead, right?
Okay.
Right. And then you can only do that trick if the lowest priority group is on a wedge, right? You cannot do that trick if the lowest priority group is on a flat bond.
Correct. Okay.
Right. Yeah. So that's the thing there.
Okay, thank you.
Yeah, no problem. So Amar, Darshan, and Kevin, I thought you guys are you going to show up for the office hours tonight? I didn't know it was going to be like a session part of your package. So we could do that for like the next office hours or something, right? Because like I thought you guys were just gonna like show up for the office hours and ask like questions, stuff like that.
Okay.
Yeah.
Do you think you could just help us maybe like a little bit with like giving us like an introduction to it? Like I guess like asking like question.
Yeah. What is the first topic or question that you want to go over?
Well, on her lecture schedule, we have before the midterm reactions of pure roles and pyridines.
Pure roles and pyridines.
And the heterocycles.
Yeah, that's what that is.
Okay.
Yeah. So is the question like the reactions of the pure roles and pyridines, or
Like maybe if you give us like a quick like introduction.
yeah, pure roles and pyridines. Okay. So pure role, furan, and thiophene are going to be very similar. They're going to be the 5-membered heterocycles, right? Where pure role is going to be the one with the nitrogen. Furan is going to be the one with oxygen. And thiophene is going to be the one with sulfur. And do you guys know what these molecules are? Are they aromatic, anti-aromatic, or non-aromatic?
They're aromatic.
Aromatic, right? Because they have a cyclic structure, planar, and odd pair of electrons, like resonating with each other. So they're aromatic. They're very stable, right? They could be formed. All of these can be formed from the Pal-Nor synthesis, right? And this Pal-Nor synthesis, the reactant is going to be a 1,4-dicarbonyl, right? And then depending on what reagent you use, you're going to get something different. So let's say we have this 1,4-dicarbonyl here. 1, 2, 3, 4. The 3 reagents that you could use to create each of these 3 heterocycles are, let's say, an amine with a carboxylic acid and heat. That would make your pyrrole because there's a nitrogen in there. The other 2 are easier to remember. P2O5 heat, P2S5 heat. Right. The oxygen is going to represent furan because it has oxygen there. Sulfur is going to be thiophene because there's a sulfur there. Right. So to predict the product here, star the carbonyls. Those carbonyls are going to be the carbons attached to the hetero atom, the atom that's not carbon, right? So this is carbon 1.
Do we have to know? Do we have to know any mechs for these or no? For these reactions?
Not for the P2O5 or P2S5, I think, because yeah, I don't think you need to know that mechanism, but you do need to know the mechanism for the amine one, unless Levin's went over it. I have to check Levin's lecture.
She'll go over it.
She hasn't.
Yeah,
she hasn't taught it to us yet. But she's gonna do both lectures and then give us the midterm. So we just wanted to like.
Oh, right. Get a head start on the thing. Right. Yeah. So that's gonna be this amine here. And then we know at carbon 4, there's a hydrogen, which is this hydrogen right here. At carbon 1, there's a methyl, which is that methyl right there, right? And so that's how you can keep track of every single group right there. So that's going to be furan with the groups on carbons 1, 2, 3, 4. 1 has a methyl, 4 has a hydrogen, and then sulfur is going to be that exact same thing right there. Right here, H and methyl on carbons 1, 2, 3, 4. Oh, wait, forgot the double bonds for hero, like that, right? So the reactivity of these things here, like let's say,
sorry. Just a quick question.
Yeah.
So you're making the pyridine. Does it have to be a primary amine?
Oh, the pyrrole here.
Or yeah, the pyrrole. Can it be? Yeah.
It has to be a primary amine because both hydrogens will be deprotonated in the mechanism in order to get this neutral pyrrole here. I'll have to double check that with you guys, because if we used a secondary amine or tertiary amine, then like because I see in the mechanism 2 hydrogens are deprotonated and we get a neutral product. And then if we use the secondary or tertiary amine, that means we're getting rid of a hydrogen. So I can see that there's a problem in the mechanism somewhere. So I'm thinking that this can only work with primary amines, but I'll get back to you on that.
Wait, can you show us the mechanism for this?
Yeah, there is a mechanism for this, right? It's first iminium ion formation, and then an acid-base reaction, another iminium ion formation, and then attack again. Do that. Wait. So a primary amine is needed to make a neutral, stable pyrrole here. Primary amine.
Okay.
Primary amine. If you didn't have a primary amine, then you cannot get a stable pyrrole molecule. Right, because there will be like an extra R group there with a positive charge. There's like no way to deprotonate this pyrrole here. Right.
So are these all just considered pyrroles? These 3?
These are considered. Let's see, what are these called? 5-membered heterocycles. Pyrrole is the only one with nitrogen.
Okay.
The one with oxygen is furan, with the F. The one with sulfur is thiophene, like thiol with the sulfur. Yeah. Okay. So I'm gonna go over this one more concept, and then I'll move on to the next question, Katia, and then go back to Ryan or Mira. Right.
Okay.
So for the electrophilic aromatic substitution (EAS) reaction for these, let's say we have a Puro here, and we try to do one of the 118B electrophilic aromatic substitution, like let's say bromination, Br2, FeBr3. But in this reaction here, the reagent is actually going to be different. It's actually going to be Br2 and some other reagent, not FeBr3 though. It's something else. It's like H2SO4 acid, right? But the metal catalyst FeBr3 isn't used in this heterocycle here. Right. Let's just use a Puro with no groups on there. This would selectively only attach to one of the carbons here, because we see that these two carbons are symmetrical. So let's say that's point A, and this is point B. Right. Point A is going to be the one that it's selected for instead of point B. Right. So the product would actually be a bromine on the carbon that is closest to the heteroatom, the non-carbon atom. So it's going to be like that. Right. So I'm going to show you the mechanism and show you why that's the case. Right. So let's see. So imagine that we have a Br2 here, and then this carbon here attacks the bromine, kicks out the other bromine. We broke the aromatic ring, right? There's a carbocation right here now. Now let's look at this intermediate here. We said that this intermediate can do resonance, which is a stabilizing factor from 118A, right? The more resonance a molecule can do, the more stable the intermediate is going to be. So we could also do resonance here again. Do that. Right. To give us a total of 3 resonance structures. This is me reacting with the point A that I labeled earlier right now. Oh, yep. 3 resonance structures here. Now, if I reacted the Br2 with point B, like let's say the furthest carbon away from the nitrogen attacks the bromine instead, this is the intermediate we get right here. And then we could do resonance with the nitrogen, lone pair of electrons. Right. And then from this point here, if we try to do resonance, like let's say we do that there, that's going to break the octet rule. We can't like go down here again because like this is an sp3 atom. And then you might think to put this double bond onto that carbon right there to give that a negative charge, but that's going to introduce like so many charges that this is unstable, too unstable to exist, way too minor resonance structure.
And so
right?
it's the fact that the positive charge gets delocalized throughout the entire ring when you reacted at that point A.
Yeah, that's right. Point A
Okay.
will give you 3 resonance structures.
Okay. And then does that also work with the furan and thiophene?
Yeah.
Yeah, furan and thiophene will have the same exact chemistry as
Okay.
Pyrrole. If you do AES on any of those 3, it will select for the carbon A, the ones
So
closest.
and then
always selects for the carbon alpha to the heteroatom.
Right. Always alpha to the heteroatom.
so is the acid used to reform aromaticity? Do you take the point from where the Br is?
Yeah,
Or
the
no,
acid or some water. It might have been. I'm not too sure of the solvent here. I kind of forgot it, but it might be acid or water, something to reform the aromaticity. That's right. Once we have like this bromine on there, we like deprotonate this hydrogen here to reform the aromaticity. It might have been water. Wait, I'll have to like review my notes on that.
Okay.
But something to reform aromaticity to tautomerize.
Okay. All right.
Yeah. but water, let's see. Or FeBr3. Let me just put this note here. H2SO4 or H2O. Okay. Katia?
Yes, hi.
Hello. What is the first question or problem that you want to go over here?
You still have like the textbook, right? Is it okay if I just tell you what problem number, or do you
Yeah.
need
Let
me
me
to
pull
send
it
it to
up.
you again?
Yeah. Let me pull up your Google Drive folder. Katia. Past resources. Lecture notes. Chapter. Oh, it was just from the syllabus.
Yeah, chapter
Yeah, there you go.
2.
Chapter 2. Okay. Let me
No,
just
chapter 3. Sorry.
Chapter 3. Chapter 3. Okay.
No, wait, yes, chapter 2. I'm sorry.
Okay.
It's chapter 2.
Let's see. Chapter 2. Uh. Oh my gosh. So much. Okay. I'm on the practice problems.
I know the pages are like all over.
Yeah, I know.
Could you go over um 42?
42. Okay. Okay, let me airdrop this to my iPad so you guys can see the problem. There we go. Airdrop. Here you go. Okay, so this question is asking us to draw electron dot structures for the following molecules, indicating any unshared electron pairs. Which of the following compounds are likely to act as a Lewis acid and which one will act as a Lewis base? Okay, so do you know the definition of a Lewis acid and Lewis base? Let's start with that.
Electron pair donor and electron pair acceptor.
Oh, wait. Yeah, which one is the electron pair acceptor? Which one is the electron pair donor?
The acid is the donor and the base is the acceptor?
The acid would be the electron acceptor.
Okay, yeah. I
The
get confused because the 3 definitions.
Yeah, Lewis, Arrhenius, and Bronsted-Lowry, right?
Yeah.
Yeah. That was a confusing concept, like at the beginning of ochem. Well, let me just give you a quick rundown of those three definitions. So Arrhenius acid is going to be a proton donor in aqueous solution. So water, alcohol, any aqueous solution, most likely water. Right. Arrhenius base. I can't remember if it's proton acceptor or hydroxide donor. It's either hydroxide donor or proton acceptor in aqueous solution.
Let me look. I have all of them.
Or proton acceptor. Either one of those. Right. Bronsted-Lowry acid is going to be a proton donor in any solution. It does not have to be an aqueous solution, right? It could be a metal catalyst. It could be well, metal catalyst is most likely Lewis acid, but Bronsted-Lowry acid is all of the Arrhenius acids plus a few more that are not in aqueous solution. Right? Bronsted-Lowry, it's more comprehensive, the Bronsted-Lowry definition, right? Because here's a chart that might help you. Arrhenius is the most specific.
Yeah, the little bubbles.
Yeah. Bronsted-Lowry is the one that's more comprehensive. And then the most exhaustive one is Lewis definition, Lewis acid, Lewis base. That's Lewis is concerned with electron movement, right? Electron acceptor, electron donors, like where the electrons are moving towards. The Bronsted-Lowry and Arrhenius are concerned with protons, right? Protons and hydroxides. maybe more so for Arrhenius, but Bronsted-Lowry might be a proton. Yeah. let me double check that. I had a very good like definition chart when I did the 118 content review sessions with a list of examples as well. Let me actually pull that up and then send it to you. So I guess
that'd be great.
You can see it, yeah. Oh, here we go. And let me send it to the notes. And then these notes will also be posted in the school community, so you can access the notes here and the recording for you to review afterwards.
Okay, perfect.
Yeah. Let's see, import, open. Yeah. Okay. Just like this is chicken scratch. Look at this here. Right. Arrhenius definition. Arrhenius acid is any substance that donates protons in aqueous solution. So here are the examples. The strong acids in Gen Chem that you had to memorize: HCl, HBr, HI, H2SO4, H3PO4, all those strong acids, HNO3, carboxylic acid. Arrhenius base is any substance that donates hydroxides in aqueous solution. So it's not going to be H plus acceptor in aqueous solution. It's a hydroxide donor.
Okay.
In aqueous solution. Right. And the examples are NaOH, KOH, calcium oxide, barium, magnesium oxide, like the strong bases in Gen Chem that you have to remember. Right. Water, this is an important note here. Water is both an Arrhenius acid and base because it's amphoteric. It can both donate a proton and donate a hydroxide ion in aqueous solution. Right. Bronsted-Lowry acid is any substance that donates protons in any solution. So all of the Arrhenius acids are the Bronsted-Lowry acids, right? But then it could be in any solution. So all Arrhenius acids, H3O plus, NH4, HSO4 minus, and these extra ones here. Bronsted-Lowry bases are any substances that accept protons in any solution. So that's the difference between Arrhenius base and Bronsted-Lowry base, right? Bronsted-Lowry base accept protons in any solution. So anything that can grab a proton, OH minus, Cn minus, N3 minus, anything with a negative charge or a pair of electrons, right? A substance can be both a Bronsted-Lowry acid and a Bronsted-Lowry base. That means that they're amphoteric. That's if they can do hydrogen bonds with itself. Hydrogen bond is any hydrogen bonded to an electronegative atom like fluorine, oxygen, or nitrogen with at least one lone pair of electrons. So like H2O, NH3, ROH, HSO4. Notice how all of these hydrogens here, they're bonded to a very electronegative atom, oxygen, nitrogen, or fluorine. Right. Now, Lewis acids and bases like is going to be the most important definition here that when you go on ochem. Lewis acid is any substance that has an empty p orbital that can accept a pair of electrons, an electron acceptor. Lewis base is anything that donates, it attacks a acid. The base always attacks the acid, a pair of electrons, right? So it will always have a pair of electrons. And here's the little bubble here. Yeah. So let's go back to this problem here. Really quick. Hello? Right here. So aluminum is a metal, right? And if you look at the periodic table, it's on the third column. So it's like boron, iron, or something like that. It would be neutral with 3 bonds, right? So we see aluminum, Br3, right? Notice how aluminum only has 6 electrons, 3 bonds. It's missing 2 electrons. That means that it has an empty p orbital. If it has an empty p orbital, do you think it would want to gain electrons or donate electrons? Like, is it like wanting to gain or lose electrons if it's missing 2?
Gain.
Gain electrons, right? Which would make it an electron acceptor or electron donor?
Acceptor.
Acceptor. So this is a Lewis acid.
Okay, I labeled that right.
Nice. That's good. Electron dot structures. So yeah, here are the electrons for B. Did you get this as the structure here?
Yes. Yeah.
How many pairs?
I was waiting for hydrogens to show up.
Yeah. Right. How many pairs of electrons does this nitrogen have here?
1 pair.
1 pair, right? And then if it has a pair of electrons, do you think it could accept or donate electrons?
Donate.
Donate electrons, making it a Lewis base. Did you put that as well for the answer?
I did.
Yes, nice. Let's see. See.
He said apparently there's a key online somewhere that I can find if I like do some digging.
Uh-huh.
So, but
Right,
I think
right.
it's just on completion, so that makes me feel better.
Yeah, and I'm pretty sure these are like correct so far. Like I'm pretty sure these are the correct answers.
I know.
That's good. So this boron here, it's one of the weird atoms that can be neutral with 3 bonds, missing electrons. So this is similar to A, making it a.
Wait, you said it's fine with 3 bonds. Oh, making it acid.
Yeah, Lewis acid because it could gain electrons.
Okay, yeah.
Okay. Oh, HF here. This is the one I'm kind of iffy on. Okay, let's see. Now, what did you say this one is?
Oh, I literally underlined them both as both because I had no idea.
Oh yeah. This F is a wild card. Okay.
Because they're both missing 1, right? So is
Oh.
the answer could just be like either? I don't know. They're both missing 1 electron to fill their shells.
Yeah, I see. HF can access space. So this is going to they're actually fulfilling all of their electrons. This fluorine has all of the octet 8 electrons, 2, 4, 6, 8.
Uh-huh.
And this hydrogen here, it only wants 2 electrons because it's in the first orbital, right? So since it's already like happy with its electrons, do you think it wants to gain more electrons, or can it donate electrons? Oh wait.
Only donate. I mean, it can't gain anymore, right?
Yeah. It can't. Right, but then let's see. Whenever I see HX, I always think of an acid, right? Like HBr, HCl, HF. Imagine some kind of base like hydroxide ion comes around, right? That hydroxide ion oxygen pair of electrons is going to attack the hydrogen right there and then kick out that bond to fluorine right there, right?
Okay.
Water, H2O, and fluoride ion, F minus, right? What did this hydrogen do? Did this hydrogen accept or donate electrons? Like what happened in this arrow here? Did it gain or lose electrons? This hydrogen here.
Lose?
Oh, well, no, technically, yeah, it lost electrons from here, but it also gained electrons from here. So
Okay, I'm like confused by what you mean by attack.
What I mean by what? Sorry.
Attack. Like
Well,
when it attack, like what does it do?
Yeah, so this oxygen here, notice how the pair of electrons of the oxygen is like attacking this hydrogen right here. Like it's making a bond to the hydrogen right there. This pair of electrons of oxygen is now this bond right there, right?
Oh, okay.
Yeah, that's what it means by attacking or making a new bond, right? So this HF here, it says it could be both a Lewis acid and Lewis base. But in
So
aqueous
both.
solution, yeah, both. But I would lean towards Lewis acid. I would lean towards Lewis acid.
For the hydrogen?
Yeah, the HX thing. Right.
Okay.
Because it's gaining electrons here. Yeah, I'm like not too sure on the HX concept of that Lewis definition. Right.
And so then the fluorine would be the base?
Yeah, the fluorine would be the Lewis base, right?
Okay.
This is both the Lewis acid and the base. The hydrogen is the Lewis acid. The fluorine would be the Lewis base.
Okay.
Right. Lewis base.
Okay. I mean, he probably wouldn't say like you're wrong if you put both.
Yeah,
like,
yeah.
Definition wise.
Right, definition wise. He can't say you're wrong if you put that like that. Like one part of the molecule is a Lewis acid, the other part of the molecule is a Lewis base. Right. What did you say this thing is right here?
Without reevaluating what I put, I put all the hydrogens as acids and I put the carbon sulfur carbon as bases.
Oh, right. So the
But
hydrogens
sure
of the carbon here are not going to be Lewis acids because when we try to deprotonate it, right, like some kind of base comes in and grabs that hydrogen, this bond between carbon and hydrogen here has to go on that carbon, right?
So then it becomes a acceptor?
An acceptor, right? and it will have a negative charge this time, right? Like the carbon will have a negative charge.
Uh-huh.
This negative charge here is too unstable to exist. So this hydrogen is actually not acidic,
Okay.
right? Because the negative charge on carbon is not stable. It's not an electronegative atom.
Okay.
Yeah. Another way you could think about it is that this hydrogen here is not attached to an electronegative atom. This is not polar bond.
Oh, okay. Yeah. I was like, there's got to be some easier trick way
Yeah,
to
yeah.
think about this. Like,
Not partially positive. Acidic hydrogens are really partially positive, like HX. Like the halogens really make the hydrogens positively charged. Right. But you look at the pairs of electrons here on sulfur. These pairs of electrons can donate, can attack an acid.
okay.
Right? Making
So-
them
Yeah. Sorry. Continue.
yeah, Lewis bases. Is that yeah, Lewis bases. This is a Lewis base here.
Okay. Yes.
Now the last one, titanium Cl4. What did you say for that?
The last one. Was there a part F? Oh, there it is. I was like, did I not do it?
Oh, this is a weird one. One of the weird ones. Think of it as a metal, like aluminum or iron.
Okay.
You have an empty p orbital.
Oh, I did the opposite of what I did for aluminum.
Uh-huh.
I don't know why. I really didn't get what I was doing when I was doing this.
Yeah, you thought because it had 4 bonds, it has all the electrons already. It actually has a missing like p orbital, empty p orbital, because titanium is one of those weird metal things. Like this is not as important like in ochem, like when you learn like future chapters. This is just like more gen chem related.
They keep throwing the metals at me. I'm like,
Yeah,
I don't
yeah,
deal
yeah.
with that part of the periodic table.
I know the metals is more for inorganic chem. Like what's it doing here in ochem? Right. And because it has an empty p orbital, will it be a Lewis acid or a Lewis base with the empty p orbital? Like that's
Acid.
missing electrons. Acid, Lewis acid. That's right. And it's actually a very strong Lewis acid. Yeah. So that's how you do that. Right. Lewis acids, electron acceptor. Lewis base, electron donor.
Okay.
Yeah.
All
Nice.
right. Thank you.
Uh-huh,
I've
no
got a
problem,
couple
Sophia.
more, but I'll just do the homework while I wait.
Okay. Okay. Amira. We could work through the
Yeah, sorry.
again.
I had another question from the exam.
Yeah.
So, general question about like number 2.
Number 2.
Yeah, so I got both of them wrong when I was doing it.
Mhm.
So like on the first one, it's achiral, not meso.
Mhm.
Is it achiral because the other 2 groups is like CH and CH2, or like they're both CH2? Is that why it makes it achiral?
Right. So the best way to think about this is convert this whole chair conformer into the flat 6-membered ring. So the way I'm going to do this is number all of these atoms 1, 2, 3, 4, 5, 6, and then draw out in this form here. 1, 2, 3, 4, 5, 6. Notice how carbon 1 there is a fluorine and a chlorine.
Mm-hmm.
This carbon here is actually not a chiral center because a chiral center needs to have 4 unique groups attached to it. This carbon here has a fluorine, but this group here is the exact same group as that.
Right, okay.
Yeah, so that's not a chiral center.
Okay.
Now, if there was something like that, then that would be a chiral center. Like if there was a methyl group like that on that carbon.
Because
Right, because this side here will have a methyl group closer to it, whereas this side here has no methyl group. Like
Right,
let me
okay.
separate them more clearly. That's one side, and this is the other side. Does that make sense so far?
Yeah, that makes sense.
Yeah, this side here will have that methyl group making this carbon chiral. Now, what if the methyl was here? Is this chiral or achiral?
Would it be achiral still?
Yeah, it will be achiral still because this side of the molecule is equally distant to the methyl group as the other side. They're both equally distant to the methyl group like that.
Okay.
Right.
And then for the second one,
Achiral and
Oh.
yeah, second one.
I got this one wrong as well, it's achiral meso. So
Achiral.
yeah, that's the correct answer. Can you explain why?
Yeah. So meso, whenever you see that, right, always think of 2 chiral centers. There's
Mhm.
exactly 2, 1 R, 1 S. But the most important thing here, what do you think? Like, what do you know about the meso molecules? Like, what is that distinguishing feature of mesomolecule.
It needs to have a plane of symmetry, right?
Yeah, plane of symmetry, plane of symmetry. Do you see any plane of symmetry here?
Yeah,
Where? Like, where's the line at?
like a horizontal line in the middle of like, yeah, right there.
Great, because everything on that side is the same as the side right here, and we do have two chiral centers, one here and one here. And if you do the R and S, one is going to be R, one is going to be S, but to save time, we can say that's meso because there's two chiral centers and a plane of symmetry down this middle here, making it meso.
Got it. And then how do we know it's achiral?
Great. So mesomolecules are always achiral.
Got it. Okay.
And the reason why is because of the plane of symmetry. The plane of symmetry gives it so that it has no optical activity. Does that sound familiar, that term, optical activity?
Yeah.
Right. Because the reason why it will have no optical activity is because, have you learned about the term levoratory and dextroratory?
Yeah, we did, I think.
Right. One chiral center, let's say it will rotate light 50 degrees. I don't know, counterclockwise. Oh wait, clockwise. And then the other chiral center is gonna rotate negative 50 degrees, like the other direction.
Okay.
So there is like optical activity for this chiral center and optical activity for this chiral center, but they're both equal in magnitude but opposite in direction. So they will cancel each other out to a net zero optical activity, achiral. Right? Because of this plane of symmetry here. So just think that all mesomolecules are always achiral because of the plane of symmetry here.
Okay, got it.
Right.
Okay.
The plane of symmetry leads to the no optical activity because they will cancel each other out. Levoratory will cancel out the dextroratory.
And then there's never plane of symmetry in chiral molecules, right?
Yeah.
Okay.
There's never wait. Sorry, say that again. Sorry.
There's never a plane of symmetry in chiral molecules.
Right.
Yeah.
Chiral molecules will have at least one chiral center, so 1 plus chiral center, and no plane of symmetry at all.
Okay.
If there are multiple chiral centers and a plane of symmetry is present, then it's automatically achiral.
Right. Can we go over like determining R and S? Sometimes I get like confused.
Yeah. Let's just go over to determining RNS practice.
Okay.
Okay, so here's my thought process on how I do this. The first thing I do is I find my lowest priority group, which is 4. Right? And then there are going to be 3 scenarios like that you could do. A is going to be the easiest one, B is going to be the intermediate one, C is going to be the hardest one. If the lowest priority group 4 is on a dash, the backside, then do everything normally. Then you'll get the right answer, RNS. And we'll do example problems with that because there are some tricky examples of assigning RNS because they could trick you with like the longer chain, bigger chain, alkenes as well. But we'll go over this concept first. The intermediate example is going to be when the lowest priority group, which I'm labeling as 4, is on a wedge. Which the process for that is do everything normally. Then flip it. So if you do everything normally and it looks like R, then it's actually S. If and only if the lowest priority group is on a wedge.
Okay.
If it's a dash, do everything normally and then it will be exactly as it looks like. Right. And then the hardest part, which we did earlier, is when the lowest priority group 4 is on a flat planar bond. Then rotate groups to make the lowest priority group a dash, the backside. Then do everything normally. Do everything normally. No flip needed after you do rotate. No flip needed. Right. So let me give you 3 different examples, and then I'll have you assign RNS and tell me your thought process on it too. And then if you mess up, I'll let you know where you messed up, and then what to think about that.
Okay.
Right. Okay. Try that first one there. Oh wait, wait. Hold on. Okay.
Okay.
Okay, let's do the first one here.
Okay. So we would do everything normal because the hydrogens and the dashed.
Yeah, the hydrogen is on the dash, and the lowest priority group does not always have to be hydrogen, because the lowest priority group can even be a methyl group, right?
Right.
Like
Yeah.
our center can have no hydrogens at all.
Right.
Yeah.
Okay. Yeah.
Yeah. Do everything
So the-
normally?
Yeah. So the OH would be 1.
Carbon. Right, because the very first atom here is carbon. If there's a tie, then we see what's attached to it. This carbon on the top is attached to 2 carbons because it's double bonded. This carbon on the bottom is attached to 1 carbon and 2 hydrogens. This carbon on the very bottom is attached to an oxygen and 2 hydrogens. Oxygen beats carbon, so that's why that carbon there is number 1. So it's not the oxygen. Don't say the oxygen is number 1. It's this carbon here.
Oh,
That's
it's the
number 1.
carbon.
Right, because it's the very, very first atom attached to the chiral center
Mm-hmm.
that you look at. Right. Some examples can be tricky because you automatically look at the electronegative atom, the most higher priority group, right? But then the other one might have been the higher priority group because of the very first atom is higher on the other end, right? So just look at the very first atom attached to the chiral center.
Wait, can you? So wait, how is the top one connected to 2 carbons?
Yeah, the just top one here is connect to actually 1 carbon, but 2 times because of the double bond. Right, because how many hydrogen is it attached to? How many hydrogen atoms?
Just 1.
Just 1, right? And then it has 2 bonds to the same carbon.
I see. Okay.
Right. Right. So based on that, which one takes priority here?
Oh, the top one.
Yeah,
The
the
double
top one.
Yeah.
Yeah, that's right. Because it's a tie. Carbon beats hydrogen, making this number 3.
So then it would be S.
Yeah, that's nice. Get it.
So we're gonna have to switch it, right? Since the
Right,
methyl
because where's the lowest priority group attached to? What kind of bond? Dash, wedge, or flat bond?
a wedged.
Yeah, a wedge, which is the methyl group here.
Methyl, yeah.
So, what's the process? Do we do everything normally and not flip it? Do we do everything normally and flip it, or do we have to rotate?
We have to flip it and then do everything. Oh, so step B.
Yeah, the other way around. Do everything normally and then flip it.
Yeah.
Yeah. Right. Okay, so what are your priority groups here for part B?
So it'd be CH2, CH3 at the top, then the SCH3, the methyl, and then the CH2 connected to a CH, and then the ethyl group.
Wait, so you're saying this is 1, this is 2, and this is 3 right here?
Oh, sorry, no. The SCH3 would be the first one.
Right, because even though this ethyl is bigger than this one here, look at the very first atom. Has a higher atomic number, sulfur or carbon?
Oh, the S is higher.
Yeah, that's right. Look at the very first atom. Even though this is smaller, what's attached to it? That's not important. It's the very first atom that's important.
Yeah.
Okay.
And then the second one, okay, this is where I'm stuck.
So there's a tie between this carbon and this carbon.
Yeah.
What's attached to this carbon here? Ignore this bond here to the chiral center. What's attached to that carbon? What atoms? What 3 atoms?
CH3.
1 carbon and 2
CH2?
hydrogens. It's attached to this 1 carbon right here, right?
Hydrogens?
Like,
I'm confused.
oh, right. Because how many hydrogens are bonded to this carbon right here?
Oh yeah. Okay, yeah.
Huh? How many?
Oh, 2.
2, yeah, 2. Right. So what are the 3 atoms that this carbon is attached to, ignoring the one to the chiral center?
2 hydrogens.
2 hydrogens and
then a carbon.
1 carbon, right? So I like to label the higher atomic number first, and then the lower ones at the bottom. Does this make sense so far? Like how this carbon here is this carbon?
Yeah.
And then these 2 hydrogens are those 2 hydrogens right there?
Yeah.
Right. What about this carbon here on the left side? What is that carbon attached to?
Also 2 hydrogens.
Yeah, 2 hydrogens and
a carbon.
Yep, a carbon. So it also has this right here. Notice how there's a tie from this and this?
Yeah.
If there's a tie, then you move on to the next atom. So it's going to be purple versus purple here. What are the 3 atoms that this right purple carbon is attached to?
It's attached to 3 hydrogens.
How many hydrogens?
3.
Yep, 3. Right. 3. So I'm going to write that as this right here. Does that make sense so far?
Yeah.
Yeah. How about this left carbon, purple carbon right here? How many hydrogens?
Just 1.
Wait, and then how many other carbon? Yeah, how many other atoms? And what is the atom?
Wait, sorry, say that again?
Yeah, so what are the 2 other atoms that this carbon is attached to, ignoring the previous bond? Ignoring that bond.
Oh, 2 other carbons.
2 other carbons, so that's CCH. Does that make sense?
Yeah.
Yeah, so what takes priority, CCH or HHH?
CCH.
Yeah, CCH. So that makes, is this carbon here number 2, this carbon here number 3. Does that make sense?
Yes, that makes sense.
Yeah. Right. Okay. So what does that look like? 1, 2, 3, 4.
That's S.
Oh, like going this way? Like what does it look like originally without flipping it? Like 1, 2, 3. Like what does this rotation look like?
Oh, sorry, that's R.
Yeah. It looks R, but it's actually S.
Yeah.
Because you have to flip it.
Right.
So you might have gotten lucky in the test, because like if you like think it's wrong and say S and then you don't flip it, then you would have got it correct still if you didn't flip it.
Yeah.
You did it wrong. You got lucky. Right, but this is the correct way to do it.
Okay.
Okay, so last one, and then I'll move on to Katya's last question, and we'll call it office hour session. Okay, so let's try this hardest example here for the RS, assigning RS.
Okay. So we're gonna have to do the step C, which is first moving the
rotating the 3 groups. So
yeah,
to do that, we have to rotate. We have to keep the other planar bond stationary. We have to keep it still.
Okay.
And rotate these 3 groups right here. What direction do we want to rotate it at to make the H on the dash on the backside?
Left?
The left this way, like this.
Oh no, sorry, the other way.
Oh, the other way. Right. Because the dash is on the other way, right?
Yeah.
Right. So when we do that, keep this side the same because we kept it stationary. Every single bond stays the same. Like the flat stays there, the wedge stays there, and the dash stays there. But what is attached to those things are different. What's attached to the flat bond now?
Would it be the wedged? It would be like
Iso.
Oh, is that
Pro.
Isopropyl.
Isopropyl.
Yeah.
Know your common functional groups. I have substituents.
Okay. Yeah, I need to memorize that.
Yeah. flashcards because that's what I did.
Mm-hmm.
What would be on the dash now?
It actually be the hydrogen,
Yep. What would be on the wedge?
the CH3.
CH3 or what is this? It's gonna be an ethyl, right? Because this stuff here is an ethyl. So it's gonna be like that.
Oh, okay. Oops.
Right. If that wasn't there, then it would be a CH3. Okay, so now we could do everything normally without flipping it. What's number 1? Yeah, a lot of carbons.
Yeah. Oh, let me see. Okay, so number 1 would be would it be the on the right?
Yep, the right. Nice.
And then the second one would be would it be the like I don't know how to I don't know how to like say what it is. The
Ring, benzene.
yeah.
Yeah. Benzene. It's a benzene.
Oh, okay. Okay. And then the third would be like the dash, the
Right.
wedge. Yeah.
And
So
that is
so that's S. So then it'd be
yeah.
R.
Oh, so do we flip it or no?
Oh, oh no, we don't.
We don't because the lower part of the group is already in the backside, so we don't flip it.
Okay. Yeah.
Yeah. So you don't flip it once you rotate it.
Correct. Okay.
Yeah. So those are the 3 cases there. I would do more practice problems with these R and S stuff. I'll actually let's see if I have more practice here, and then you could like access them through the school community and practice it with the key. But let me see if I actually have it here. Discussion, problem sets, notes. Those are my notes for the 20 assigning oranges. That might have been this one. Nope. Fast free radical halogenation. Oh nope. Wait, hold on. Maybe. IR. No. That's way before 7. Oh, here we go. Yes. Okay, here's a lot of practice. I'll send you the field notes so you can see the. But actually, I'll send you the outline and the key as well. Yeah, outline so that you could do it without looking at the key, and then check the answers with the key afterwards.
Okay. Thank you.
Anti-note, import, done.
Where would I find this?
This would be on the school community under the summer session 1 2024 modules.
Okay.
Right. Like if you go to classroom, you see a classroom tab. Like in the school page.
Under classroom summer session 1, and then
week I'll make another page for week. What week are you guys on? Week 4, week 5?
we're starting week 5. Yeah, this is week 5.
Week 5, okay, yeah. There's gonna be another page for week 5, and the recording and the notes are gonna be there with the practice.
I'm only on week 2.
Okay.
You're on week what, Skatia? Oh, week 2? Oh yeah, because you're taking it at community college, right?
Yeah, it's only 5 weeks though.
5 weeks, dang. That's fast, faster than the UC Davis one because it's 6 weeks over the summer.
And it's a semester into 5 weeks. Like imagine 10 weeks into 8, that's like easy, but like 17 into 5, I'm like,
oh, that's crazy. Yeah. Okay. Any last minute questions on that, Amira?
Can you just go back to like the chart you made for me with like the shows of rules? I can just screenshot it.
Yeah. When is your next midterm? Like when's the date?
This Thursday.
This Thursday. Okay.
Yeah.
Yeah. So maybe like to practice more, you can show up to like tomorrow's and Wednesday's office hours.
Yeah,
same. I also have an exam on Thursday.
On Thursday? Yeah, Katia too.
All right, thank you so much.
Yeah, I have 2 quizzes this week too, actually. One tomorrow and one on Friday for my chiropractic school.
Oh goodness, good luck.
Thank you. Okay, I'll see you tomorrow, Amira. But
See you.
Katia, I'll help you with one more concept or question with practice, and then what color session. And then we'll
Okay,
talk-
sounds good.
Yeah.
Thank you so much.
no problem.
I was just, I mean, I had like a couple other questions with the
Uh-huh.
acids and bases, but I think I'll probably be able to figure it out. So I was just starting chapter 4's homework.
Yeah.
And it asked me to draw 2 different structures for glucose. So should I just assume that I should be trying to draw a chair?
Yeah.
Okay.
And you know the
And
two
then,
different
like-
carrier flips.
Yeah, we
Uh-huh.
just went over it today, but I think I'm getting it.
Right. So
Look at you draw that. That was impressive. People don't give you enough credit for that.
oh, it's just repetition, you know?
That's crazy.
Like when you first learn it, like you gotta like be careful with all the angles and then all the like parallel lines and everything. But then
Yeah, he's like, so make 2 parallel lines. Okay, I did this one. I thought it was pretty good. If it'll,
and
yeah.
then here are the equatorial ones. Oh wait, hold
I made one good one and I'm just copy and pasting it.
on. And here are the exact numbers to like the correct rotations as well for it.
Okay, yeah. So you start to, oh, he numbered it opposite. He started with the top right today. I swear to you.
Wait. The numbering system doesn't actually matter here.
Oh, okay.
Right. The thing that matters the most is the groups that are attached to the number. The way
Okay,
you
yeah,
number it,
because they just like rotate.
yeah,
much.
make sure you
Yeah.
rotate it the same way, however you number it. But this is my numbering system. You can follow
Okay,
his,
cool.
mine, or you make up your own. Or
That's
whichever works
fine.
best
They
for
do
you.
the same thing. It's all good.
Yeah.
I was like, wait.
I know. Like, what is going on here? And an important concept for this chair conformer flip thing is that let's look at carbon 1. What is going up at carbon 1? Axial or equatorial?
What's going up?
Yeah, what's going up?
Equatorial. Like it's
Right,
on
so-
the top. It's on the top side. Yeah.
Axial is the one that's going directly up and down.
Oh, up and down. Yeah, that
Oh.
axial one. Sorry, I just thought you meant like top or bottom. I was
Oh,
like,
yeah. Equatorial is going down. Axial is going up on this flip here.
oh, on that one, I was looking at the second one.
Oh,
my
you look
goodness.
at the second one here.
Yeah. Yes.
No, on the left one. Right. On the one on this one here, it is gonna be the equatorial that's going up.
Yes. Okay.
Right.
Okay. Cool.
So here's that concept here. When you do flips, right? You maintain direction, like up or down, on a group, but then you flip orientation, axial or equatorial. So let's say, for example, we have this flat cyclohexane ring right here with only one substituent to like show this easily. Alcohol, which is a wedge. And let's say that's 1, 2, 3, 4, 5, 6. Is the wedge going up or down?
Up.
Up, right? So on this conformer here, that alcohol is axial.
Okay.
But everything else are hydrogens. You could erase the bonds, but I'm just gonna put hydrogens here so you could have reference on what is what.
Mm-hmm.
Right. But on the other flip, when we flip it, where is the alcohol now? Is it gonna be axial or equatorial? We want to maintain direction. We want to maintain it going up. So what's going up?
Equatorial, right? 'Cause
Equatorial, right?
switches.
So that's what I mean. Like when you do flips, the direction of the group always stays the same. So the alcohol stayed up, but the orientation,
Like top or bottom, as in like
top or
up,
bottom,
right?
right?
Yeah. Okay.
Top or bottom always has to stay the same. But axial equatorial will flip in between conformers.
Okay. Yeah, that wasn't too difficult for me to understand, but I'm
Uh-huh.
sure it'll get harder. I'm like, do-do-do.
Yeah. Tomorrow, if you come to tomorrow's office hours, I have a lot of practice lines with these chair conformers and flips with like the axial equatorial, like which one is the least stable conformer, which one's the more stable conformer, which one has less energy, more energy.
Yeah.
Yeah. If you went over that, I already have a lot of practice on that on this topic here.
Okay, good.
Yeah, and then if you schedule in your 2-hour session this Saturday, we'll go over those as well if you want to.
Okay, yeah, I'm sure we'll have covered like 2 more chapters by then. So
Yeah.
we'll have a lot of
Super
stuff to
fast-paced.
talk about.
Yeah, is your life so far been ochem?
Oh yeah, well, I work in the morning, so like if I
Oh.
want to do anything done, I have to do it before I go to work.
Before you go to work? Oh my god.
Yeah, and I work starting at like 8, so there's like that's why it took me like probably like 8+ hours to do all 3 chapters of homework and then 4 hours on the lab report.
Oh my god, yeah, because right after this office hours, you know how my quiz tomorrow. I'm like so behind right now. I have to like catch up on every lecture notes. I gotta like figure out a way to like study this efficiently. So I'm ready for the quiz tomorrow.
Oh my gosh, that's crazy. Are you
I
like going
know.
in person? Does it start in person or?
Yeah, it's in person. Yeah,
That's why they're late. Okay. Oh my
Yeah,
gosh, you're doing
yeah.
like the same thing as I am right now.
yeah. We're just together. We're not alone. We're not alone.
Yeah, no, we're just doing both.
Yeah.
Jack of all trades.
Uh-huh.
Okay, so yeah, so asked me to draw 2 different structures for glucose. So first I drew a flat one with like double bonds, but I'm assuming that's completely wrong. Like I didn't draw a chair. And then I drew a chair.
Oh, wait. So glucose is the sugars one. This is the regular structure for
Yes, I looked it up on the
okay.
lecture slides.
Wait,
I found
think
that.
of glucose as the all equatorial sugar. All of the alcohols or every single
I
group are
noticed that. Okay.
equatorial.
I was like, that's so weird, but
I
it's
know,
the
I know.
most stable, I'm assuming.
Most
Because they're
stable.
farthest away from it. They're not having eclipsing with the stuff.
Yeah, not eclipsing, right. That's good. That's one thing that axial strain. We don't want the groups to be axial and eclipse to each other to have steric hindrance. That's good.
Yeah.
We want it to be equatorial to avoid eclipse, avoid steric hindrance. Right? But
Okay.
this one right here, it's not an alcohol, it's a CH2OH, which is why it has an extra arm there.
Oh, okay. Yeah, I think I copied that wrong. Yeah. Okay, let me fix that real quick.
Now the other flip, let's see. Let's do the same thing. That's it. We said this was 1, 2, 3, 4, 5, 6. This is gonna be oh no. Yeah. This is gonna be 1, 2, 3. No, oxygen's not gonna be there because 6 is on here. There you go.
Wait, what?
What did you put?
I rotated it clockwise. So I put it in the 4 position on your second drawing.
Wait, hold on.
That
was the same show, the same flip I drew earlier. This is the other flip, right?
Yes.
Wait a minute. 1,
I don't know.
2, 3, 4. Wait, 1, 2, 3, 4.
I drew like a flipped, so I drew the chair in the opposite orientation as your chair first, and I put them axially, and then I'm assuming that's gonna be less stable compound, and then I flipped the chair, and then I put them the proper way equatorially. Does that make sense?
Can you send me a screenshot through text message so I can see?
Yes, of course. I might have to take a picture of my iPad because my iCloud doesn't like to jibe with itself. It's like I don't have any storage. It doesn't
any storage on your iPad?
No, so it doesn't sync to my phone. There we go.
Let's see.
You should send.
Okay.
And now that I'm like caught up, I'm like trying to do the homework at least a little bit each day, so I don't have to spend like my entire weekend doing it.
Entire weekend doing it, right.
It's horrible.
That's smart. Let's see. What's your clockwise? Oh, right. So is there a big one on the bottom, the other version of it?
That's the version I
That's
copied from the
normal one.
slides.
That's normal one,
Yeah.
right.
Yeah.
And then the flip
that's
one
your
is
number
the
one.
other one. So 1, 2, 3, 4, 5, 6. So you notice how when we do this conformer from here to here, we rotate every number clockwise. Like
Yes.
this one went here. Notice how at this position here, we have to put the oxygen right here because when we rotate everything clockwise, the oxygen is going to be right there. So that's why the oxygen is going to be at that position here.
It does?
Right, because if you look at yours right here, right, like I'm going to put it in pink.
Isn't that counterclockwise?
Going this way is clockwise.
Right. But why wouldn't it go down?
It wouldn't go like down
like towards us, I guess. Like to the spot that I put it in, I guess.
Oh, this one right here?
Yeah.
Oh, so yeah, this is another important thing here. from this conformer here, where you know how the slant is going from like this right here, like on the left side,
Yeah.
going from here to here is clockwise. Going from the other one to here is counterclockwise.
Oh my gosh.
So
So I
that's
just
the other
screwed
important
myself
concept.
up. Okay, whoa.
Yeah,
That's
right. Because the
ridiculous.
sugar one starts with this weird one here. The one we're not
Okay,
using.
so how do you remember that? Like with like the direction of the slants? Like
So the way I like to think about it, right, is like, you know how you have this one right here? Imagine rotating everything clockwise, like with the wheel.
Okay, because it's
the
going
wheel.
that way. That's the way
Yeah.
it's pointing.
Right.
Okay.
You do
And
it
then the
that way.
other one, the opposite. So whatever
Yeah.
you start with, rotate the direction of the angle.
Yeah, yeah.
Okay, I like that. Perfect.
Yeah,
I
like
knew
the
you
wheel,
would. I
driving
knew
a
you would
car.
have something to remember it.
That's good. That's good. Wait, let me draw a car wheel. Oh, car wheel. That's so bad.
Oh, that's perfect. It's beautiful.
Yeah, so it's not that. Okay.
That's important to know. He did not say that today.
It is important to know. There are actually a lot of like small details that professors do not go over, but you'll figure them out by yourself and make little tricks by yourself, and like your little mnemonics, little tricks to remember things by yourself as you do more practice and figure that out, right? Because
Or
professors
by
don't know.
failing on the exam. That's
Yeah,
not
like
what
they
I want
already
to
see it,
do.
but you don't see it yet, right?
Yeah, I'm like, excuse me, I haven't been doing this for like 12 years.
Yeah, I know.
Okay.
Uh-huh.
So then, okay, so the two different structures would end up looking like the ones you have on the bottom.
Right, right.
Okay, and then the more stable, so just basically axial or equatorial, and then make sure you're rotating it the right way because I
Right.
didn't.
Mhm.
And then the more stable would be the equatorial, right?
Right. And notice how
Okay.
all the things remained up or down, but then the orientation just changed.
Yes.
Yeah.
Yeah. Okay. All right.
Yeah.
Yeah, I think
Uh-huh.
that's it for the like naming. It's just like you just name it.
Yeah, yeah.
Yeah, I think
just
it's pretty
on the
normal. You just
system.
add the cyclo in there, right? It's the same
Yeah.
thing. Okay. Yeah,
Right,
that
right.
was my next problem I'm on.
Uh-huh.
Perfect. Thank you
Yeah.
so much.
No problem. I'll maybe see you tomorrow or this Saturday for our session.
Probably, yeah.
Yeah.
Okay. Thanks. Bye.
Bye.
Good luck with your quiz.
Thank you.
Of course.
I'm gonna need it.
Oh yeah. If you have any questions, I can ask my dad for you.
Oh yeah. Yeah.
Okay.
I'll let you know. I'll let you know.
Of course, yeah. Bye.
Bye. Hey Ryan.
Hello.
Hey,
What's
sorry for the
up?
wait. Sorry for the wait. There were a lot of people today and today's office hours.
It's okay.
Yeah.
It's still within my schedule.
Long time no see. Like it's been a while since we talked to each other.
Yeah, it's been a
Yeah.
while.
Like your schedule changed a lot, I bet, and my schedule changed a lot because you know how before my office hours was at a different time, but then I switched back to the old schedule, 9 to 10. So
Yeah.
I've been experiencing with my schedule as well. Like, what's your schedule right now?
Wake up at 6, sleep at 10.
Wake
But
up at
even if I
6.
don't sleep at 10, I still get like 7 hours.
Yeah, and you wake up at like 5, around 5.
No,
Yeah.
no, it's 6. Well, yeah.
Oh, 6. Yeah, that's like 8 hours, but then like at least 7 hours of sleep, right?
Yeah.
Yeah.
So like on a scale of 1 to 10, how behind are you on assignments? Because I was like overhearing everything.
Probably like an 8 actually. So there's a lot I have to do tonight to study for tomorrow's quiz. So I'm gonna try to finish everything by midnight or 1 and then sleep like hit the thing or like yeah something like that. But it's not that bad. Like everything is just 2 or 3 lectures, so I could do that. I could catch up. I have a plan. I have a plan. Because this is just the third week of my Cairo school.
Oh yeah. Oh
Yeah.
yeah, that's like where we left off like 3 weeks ago.
Yeah, 3 weeks ago, right?
Yeah.
Dang.
Huh. I
Have you
mean,
been
I got
working
like
out?
yeah, sure. I have
Uh-huh.
a pull-up bar in my room now,
Yeah.
but let's see. Has anything changed in the past 3 weeks besides chiropractor school?
Has anything changed? I don't live at Davis anymore. I live at San Jose, so I live at my hometown. So my parents can like make me food. I live at home. I just commute to school there, so everything's like much more easy for me. I only tutor privately on Zoom now because I'm not at Davis anymore, so I can do in-person sessions. I
Ooh.
still keep my office hours, but like I haven't been having office hours since like the last 2 weeks because people didn't have midterms, but they're having midterms this week, like you see. So that's why a lot of people are
Yep.
showing up again because they have midterms coming up.
Yep.
Um, what else? I've been hanging out with my dog more, spending time with him and my friends and family. I watched Cobra Kai, the new season that just came out on Netflix.
Wait, what? I thought it didn't release till August or something.
Oh no, the new season got released. The first 5 episodes of season 6.
Jeez.
Yeah, but the last 5 they didn't release it yet.
Hmm.
Yeah. Has anything changed for you? Like how have you been?
So let's see. Almost like I guess it's just like 3 days ago. It's just like just trying to work on consistency, and then like I just like decided that I'm just gonna study for like um AP Ling and then pre-calc to like this entire week
Oh,
because
right,
like
because you have summer homework for those AP classes, right?
I mean it's not a lot. It's just memorizing, but it's not summer homework. I'm just putting it on myself to self-study.
Oh, right. You're just doing it yourself, like for to get ahead.
Yeah, but it's been good for the past 3 days because I don't know what I've been doing for the past 3 weeks.
Uh-huh.
Yeah,
Um,
because it's like I'm just locking in like now, I guess.
yeah. That's good. That's good.
Yeah.
You're like fixing up like your sleep schedule, your mental health probably, and everything in general in life.
Mm-hmm.
Yeah, that's good. That's good.
Hmm.
Have you been making new friends with your neighbors or hanging out with them?
Hanging out with them. The thing is, I've kind of been like stopped, but like I've just been like going on like the grind in the morning where I just like work out at home instead.
Uh-huh.
But it doesn't really stop like doesn't like change like how I like interact with people. Cause like I mean, if I learned how to interact with people, I'd probably interact better. But like I probably don't have that option because I'll like, have like the either I have like Discord calls with random
Uh-huh.
people and then like Zoom meetings with you, I guess. I don't know.
Yeah. Like just like talking,
Yeah.
talking. Yeah. Hey,
Mm-hmm.
dang, it's good. Have you started on looking at AP Chem stuff, AP Chem material?
Yeah, I've been using like apchem.org and then like that free website is just like
Yeah.
I need to relearn how to take notes again because I can't do it linearly. Like I
Right.
can
So
just
you've
like
been actually using that website, the
y-
apchem.org.
yeah, I forgot like the other AP Chem materials.
Hmm. Khan Academy, it's a good resource.
Yeah.
Hey, that's good. That's good. When do you start school again?
Like August 8th. Like
August
this
8th.
yeah.
Dang, so that's like less than a month away.
Maybe yeah. I'm not sure when we'll get our schedules, but it's probably gonna be next week.
Oh, for your junior year of high school, right?
Yeah.
Yeah, dang.
Got any last minute advice for junior year high school?
I would say spend a lot of time with doing clubs, extracurriculars, make connections with people, talk to your teachers a lot, be involved in a lot of things. But then don't like spread yourself thin. Like do that at the beginning, and then stick to the ones that you resonate with, that you enjoy doing, and then drop the other ones that you don't like doing. Um, what else? Study for your classes. That's like a obvious one. Um, and junior year, that's when you start like doing research for colleges because you'll be submitting your college applications right after junior year or the beginning of senior year. So you don't have to do the college research at the beginning or even the middle, but towards the end of your junior year and the summer between junior and senior year, that's when you gotta like start applying for colleges, make a whole list of it, like if you want to stay in state, out of state.
Mm.
What else? Yeah, what did I wish I did in high school? Are you in any sports, like any sports team?
Tennis. I've been in it
Tennis.
like last year.
Last year, yeah. So yeah, stick with that tennis thing. Because I really missed my wrestling team when I was in high school. Like all the memories I made from practice after school, the dual meets between different schools, the tournaments, like those, and making memories with your teammates there. Those were like the best memories I made in high school. So stick. I recommend sticking with the sport and team.
Hmm.
Yeah,
It's kind of like all the clubs are dying, but that I hope that like me being there could like revive them. But
yeah,
yeah,
yeah.
hmm,
That's good. That's good. And maybe you could even be an officer for a club.
hmm, maybe, but like we had to do that like the like last year, like where they had like surveys out. Hmm.
Last year they had to do a survey for.
Yeah, like you want to be an officer, sign this survey.
They made you sign service. Like they don't have an application for it, an interview process. Like it's just
Oh,
a
there is an interview process for
interview
some of
process.
them.
Yeah, dang. Are you in any clubs right now? Like, are you involved in any clubs right now?
Yeah, but I forgot the names of them because I've been away from school for so long.
Oh yeah, yeah. That's right. That's right.
But you know what's funny?
Uh,
I'm like born in January, and
oh,
basically, yeah, and
uh-huh,
basically what is that like I turned 17 like at the start of like January next year,
uh-huh.
and like it's like damn, I gotta get a job. Like reality hitting too fast.
Yeah. Don't worry. Like
Yeah.
I never had a job until I started tutoring for my university when I was 19, 20 years old. So yeah, yeah, don't worry. But um if that's what something that you want to do, then go for it. You know?
Nah, it's just like fear of unknown stuff, like you don't know what's gonna go on. Like you're just being dumped into this new world. It's like, oh shoot, it's happening.
I know, like becoming an adult, right? Like
Yeah.
after that. Um yeah. And then like you don't know where like you're gonna go for college yet. Like are you planning to apply for in-state like nearby colleges or like out of
Um,
state when you're gonna move out?
I'm saying in-state.
In-state, okay. But like far away, like maybe LA or Irvine or something
I'm
like that, or
saying
far
I
away.
think my dream school is gonna be UOP.
Oh, UOP, that's your
University.
dream school.
Yeah.
Uh-huh.
But
And
like
then
I'm competing with people like coming from Canada and everywhere else, not just like
I
where I live.
know, yeah, not just locally, it's international as well.
Yeah.
Right. That's crazy. Yeah.
I think I'm gonna become a dentist.
Oh, a dentist? Remember Joseph Nguyen, my friend that joined the office hours like a few months ago, and you saw him.
Hmm.
He wants to become a dentist as well. So maybe I could connect you with him, and he can give you advice for dental stuff.
Hmm.
Yeah,
Yeah. Did you like meet Joseph like in high school or is it college?
yeah. He's a high school friend. We went to different colleges. He went to SJSU, San Jose State University, and I went to UC Davis. But we went to the same high school in San Jose.
Mm. Hmm.
Dang.
Got those connections. I'm struggling with those because I feel like alienated by like biotech, but like I'm trying to uh like make myself part of the group now since I've been at it for like 3 years now.
I know, like,
Freshman through junior years, like you got to make friends now.
you
Yeah.
freshman to junior year, right, right. Dang. Let's see.
Hmm. What are you looking around your room for?
Because I have like pictures of my like wrestling team. Like we were just talking about it, like wrestling team portrait. My high school like senior poster that they made for me. I was like, oh my god, all these memories are coming back to me now. Like just by talking about it with you, I was like, oh dang,
Mm-hmm.
I missed these memories.
Mm.
Right, like I got this trophy for wrestling in the wrestling team.
Damn. Like what? Like the first place? Wait. JV most outstanding wrestler.
Right, that was my junior year, 2018 to 2019.
Mm-hmm.
2019 to 2020, that was my senior year, and that was when I was in varsity. But I fractured my right collarbone, so I couldn't wrestle anymore after that incident.
Damn, like
Yeah.
around your neck?
Yeah, around my neck, like right here.
Did you have to like wear that like
Sling, arm and
like
sling thing, yeah.
yeah.
Hamstring. Yeah. Like the guy threw me down 3 times. At first, I didn't feel anything because all the adrenaline was rushing through my body, so I felt no pain. But after like a few minutes, like the pain started coming to me, and I couldn't lift up my arm for like a few weeks.
That's tough.
Yeah, but I did still support my wrestling team by going to the dual meets tournaments and watch the games to support them.
Mm.
Yeah. Dang.
Yeah, I think my problem is just I need to make more connections with people.
Make more
And that's
connections with people.
yeah.
Like I would say like all this tutoring stuff made me more an extrovert because back when I was in high school, middle school, I was an introvert. I did not like talking to other students, other teachers, and stuff like that. Like I was like very shy. But then like now I would say like I'm like more talkative than I was before, you know. And it's very important to make connections because you never know what they can help you with, like what resources they can bring, what opportunities they can bring, you know.
Mhm.
Yeah. Right.
It's like I just like have a clean slate, I guess.
Yeah. Well, we got each other as a connection, so that's good.
Yeah, that's very fortunate.
Dang.
Mm.
Good, that's good.
Yep. I think I'll see you tomorrow.
Yeah, I'll see you tomorrow for the office hours, and then if there's like a book session, I will tell them it's 9 to 10 p.m. and then after 10 p.m. we could like catch up, talk a little bit more, you know.
Mhm.
Yeah, and you
Yeah.
said you're in the Sacramento area, right?
Yeah, I'm Sacramento.
Yeah, maybe like someday me, you, Joseph can like hang out if you're like down for that or something, you know.
Maybe when I'm like 18 or
18,
something,
yeah,
like
yeah,
out
yeah.
eating out. It's
Right.
like, hey, Dad, I'm gonna go with these people who
Yeah,
are like
that's
6
kind of
years older
sketch.
than me.
Yeah, that's sketch. That's sketch, huh?
Yeah.
Yeah. Because I'm actually visiting Davis this Sunday to deliver my Brian Ochem hoodie merchant and take pictures with them. But I probably won't visit you because yeah, you're not 18 yet. But like when you're 18 or something like that, maybe we could like hang out in person with Joseph and you know,
Mhm.
yeah.
Yeah.
Uh-huh.
Mhm.
Okay, I will see you tomorrow, Ryan. It was nice catching up with you today.
I was catching up with you too. Good luck on that quiz.
Yeah, thank you, thank you. Good night.
Yeah,
Good night.
you're gonna need it.
Yeah, I know. I'm gonna need it for sure. Oh my gosh, kind of stressed, but I got it. I got it. I'm gonna do it.
You got this.
Yes, thank you. Yeah.
Bye bye.
Bye.